Hello viewers, in this video we'll go through Cambridge A-Level Further Maths Component 2 of the Variant 1 October-November Winter 2025 series. We'll pick off with question 5. Question 4. Question 4. So, the question presents us with a second order differential equation which is not homogeneous. So, if it's homogeneous means they will equal to 0. If it's not homogeneous, so there will be a function on this right hand side. So, as you have been taught, the solution to this non-homogeneous second order ODE will have two parts to it. So the solution of this will be y of x, right? So the y is the dependent variable on x, and it will form of two parts: homogeneous part yh of x and the yp, the particular integral. We will start with finding the homogeneous part first by setting this entire differential equation and ignoring this secondary function here. So for homogeneous part, let me just write it down. So we set the differential equation to be equal to 0, and we assume, okay, for this type of second order ODE, we assume yh of x to be a form of e to a constant x. Right, so this constant can be anything. Usually I think they use gamma, right? So when you differentiate it once, okay, because of it's an exponential function, it will be the same except you multiply by whatever is the differential of the function. So in this case, it will be gamma e gamma x. And if you differentiate again, the second derivative, so it's a d squared y dx squared, it will be gamma squared because you multiply gamma again, e gamma x. Now, what we can do here is we substitute all of these expressions back into the original differential equations. So we'll get something, okay, something like 5 gamma squared e gamma x, and 2 gamma e gamma x, then finally e gamma x equals to 0. And since this e gamma x term is in each of the terms, we can factor it out, right? Factor it out of all the terms. So we have a quadratic equation in terms of gamma in the middle here, which we call this, actually this is our auxiliary equation. So we call this the auxiliary equation. And since we know also that e to the gamma x, the exponential function will never tend to 0. I mean, it will tend to 0, but it will never be actually equal to 0. Okay, so the only other possibility will be that this auxiliary equation is equal to 0. So to solve it, 5 gamma 1, 5 gamma squared 2 gamma plus 1 equals 0. We will use the quadratic formula. So you can't able to factorize this. Okay, so negative b plus minus b squared minus 4ac. Then everything divided by 2 of a. And you get negative 1 over 5 plus minus. In this square root, there will be a negative 16. So this negative 16, the negative will become the imaginary part. So it will just be plus minus 4 over 10 and the imaginary unit here. So this 4 over 10, you can simplify it to be 2 over 5. And since, okay, the auxiliary equation yields us imaginary roots. For imaginary roots, remember, you have three conditions. You have real roots, repeated roots, and imaginary roots. For imaginary roots, the solution of y homogeneous x will be whatever is in the real part, we have e to the power of that multiplied by x. So we have e to the power of negative 1 over 5x here. That's the real part. Everything multiplied by a constant of a cosine of the imaginary part. So the 2 over 5x. Then the c2, another constant, sine of 2 over 5x. Okay, so that is something unfortunately you have to memorize. So there are, I mean, for the real roots and also for the repeated roots, you also have to memorize. They have different form. So this is something that, yeah, you have to memorize. But that's all for the homogeneous part. we'll move on to the particular integral. So for that one, we will have to use the method of undetermined coefficient. So for particular integral, we use undetermined coefficients. And this, whatever the function that we assume to be the solution, yp of x, it will be depending on the right hand side of the function. Whatever the function is here, we will have to assume a different form of the solution yp of x. So in this case, the function here is a polynomial. We will assume yp of x to be the same order of the polynomial but with unknown coefficients, right? So we will assume there will be, since we already use C1, C2, we will use C3, and the order here, the highest order is x squared, so we also assume the highest order x squared, and C4x plus C5. Okay, so it is just a polynomial we assume to be a solution to this differential equation. And if it's for let's say exponential, if this function is exponential function, you would assume it to be an exponential function. If it's a trig function, you'll be assume it to be a sum of the sine and cosine. But in this case, it's a polynomial, so we assume it to be a polynomial of the same order with coefficients that we don't know. And so we can take the derivative. The first derivative, there'll be 2c3 c4, and c5 just disappears. The second derivative, it will be just here will be have x, right? Yeah, I missed out that, so it'll be 2c3. Alright, and we can substitute this back into the original differential equation also, and in this case we do include the function on the right hand side, so it will have be 5 2c3 2c3 x plus c4, and lastly it will be just the whole thing, right? c3x squared plus c4x plus c5, and on the right hand side is the function 5x plus 3. Okay, and at this point we will try and just simplify the expression a bit. And what we'll do is collect the terms with the same variable on the left hand side. So all the x squared, it will just be c3x squared, and x, they have 4c3 plus c4 x, and for the constant term 10c3 2c4 and c5. And yeah, the form of this is similar to the right hand side, and the left hand side and right hand side is similar, right? Because you have the x squared, x, and then the constant term. So we can go ahead and compare the coefficients of each of the term. For x squared, we have we have c3 equals to 1, right? Because on the left hand side c3, on the right hand side is 1. Then for the x term, you have 4c3 plus c4, we can equate it to 5. So yeah, c4 is also 1 actually. And lastly, for the constant term, okay, you have 10c3 2c4 plus c5 equals to 3. And c5, you get -9. Okay, so for your particular integral yp of x, we will just rewrite this thing, but with the coefficients is already there. So c3 is 1, so it's x squared. c4 is also 1, so it's x, and c5 is -9. So your whole solution, right, y of x, it'll be based on the superposition principle, the YH, the homogeneous part, and the YP, the integral, the particular integral. So you just add them together. So where was it? This one, YH e negative x over 5, C1 cosine 2 over 5x plus C2 sine 2 over 5x. And we add the particular integral x squared plus x minus 9. So we're not finished with the solution here yet because we still have two unknowns. You can see the C1 and C2, they are still the constant of integration that we still don't know. So what we can do here is the question given us the condition y of 0 and dy dx of 0, it will be equal to 0. So we will have to differentiate this expression later, but let's just deal with this one first. Y of 0 will be equal to 0, right? So there's the condition they give us, the boundary conditions, they call it. So we will substitute everything with x to be 0. So E0, C1 cosine 0, C2 sine 0, and x squared x also goes to 0, so I'll just write that -9. So cosine 0 is 1, sine 0 is 0, so this entire term disappears, and e to the 0 is 1. So we just have a c1 equals to 9. So that's the first constant that we found. Now we're moving on to the second condition where we have dy dx evaluated at 0 is 0. So we first have to find expression for dy dx. So it might seem, I mean, it's a bit messy, but the differentiation is not too difficult. It's just a product, so we have to use the product rule here. I'll first differentiate the exponential here, so it's a -1/5 e negative x over 5, and I'll leave the sum of the trig, just leave it as it is. Now I will leave the exponential term, then I'll differentiate the inside here, so it's a negative 2/5 c1 sine 2/5 x, and this sine becomes cosine, and I multiply again the inside, so 2/5 c2 cosine 2/5 x, and this polynomial at the behind here we just differentiate as usual, so 2x plus 1. Okay, so this is the expression for the derivative, and we evaluate it at x equals to 0 equals to 0. So 1/5 e to the 0, c1 cosine 0, c2 sine 0, e0, and this sine 0, wait, 2/5 c2 cosine 0, and 2x, I'm not going to write it, just plus 1 equals 0. And yeah, let's see where this simplifies to. E0 is 1, sine 0 is 0, cosine 0 is 1, E0 is 1, sine 0 is 0, cosine 0 is 1. So all we have here left is -1/5 c1 and a positive 2/5 c2 plus 1 equals to 0. Since we know c1 already, c1 we found is 9, so we can solve this c2 to be 2, I believe. And if we sub 9, then bring it over, then yeah, 2. And for the final part of the solution, you just have to rewrite everything as a function y of x, right? So that is the particular solution. So we have to explicitly write the function y as a function of x. So yeah, we have e negative x over 5. Then the c1 we have 9, cosine 2/5x. c2 we have 2, sine 2/5x. Then we have the particular integral x squared plus x minus 9. So this will be our full form of the final answer to this second order differential equation. Okay, so we'll continue with the rest of the questions soon, and thanks for watching. So stay tuned.